Welcome viewers, welcome to my channel MRK Techno. In today's video, I am going to discuss about fluid properties, which is continuation of my previous video, and types of fluid flows. So let us start today. Do subscribe to my channel and share my videos. We were discussing about the properties of fluid and derived equation. So tau equals to mu into dv by dy, which is the velocity gradient. And here if you take mu equals to tau into dy by dv. So this is the dynamic viscosity, so for which we got unit as Newton second per meter square, or you can write it as kg per meter second. So this is dynamic viscosity, and if you take the kinematic viscosity, mu equals to mu by rho, which is the unit is meter square per second. So this unit is a very big unit. So generally liquids or gases we use a small unit centimeter square per second. So this is about dynamic viscosity and kinematic viscosity, and this is the Newton's law of viscosity. So based on this, so whenever there is a shear stress applied on a fluid, so it should have the velocity proportional to velocity gradient dv by dy. So such a kind of fluids are called Newtonian fluids. Newtonian fluids. So whatever generally we see in our lifetime, we mostly deal with Newtonian fluids and non-Newtonian fluids. So where this tau is not proportional to dv by dy. So generally, if you apply some shear stress, and there will be some deformation, so velocity gradient will exist. But sometimes if it is proportional, we are calling Newtonian fluids. If it is not proportional, we are calling them as non-Newtonian fluids. So Newtonian fluids and non-Newtonian fluids. So if you take generally the graph here, so if you have the velocity gradient on x-axis dv by dy, and here the shear stress on y-axis. So generally if you take Newtonian fluid, so it is having a straight line. So since it is proportionate, so you will get a straight line. You can define in geometry with a simple straight line equation, just like y equals to mx plus c. But if you take this is Newtonian category. But if you consider non-Newtonian fluids, so non-Newtonian fluids, they don't follow proportionality law. So they will be somewhat a curved kind of nature. So you have to define this non-Newtonian fluids with some kind of partial differential equations of second order or third order. Okay, and another kind of fluids exist, plastic fluids. And another category, thixotrophic fluids. So plastic fluids, if you see, you need some kind of minimum stress, which we called as yield stress, in order to create a deformation. So for plastic fluids, unless you don't reach a point of yield stress, they will not show any kind of velocity gradient. Okay, and here the ideal fluid category exactly exists on x-axis, and the solids exist on y-axis. So here ideal fluids, in the sense they doesn't have viscosity, and also they don't have surface tension. So ideal fluids generally do not exist. Okay, it's a theoretical concept. And here solids, they does not show any deformation on application of yield stress. They does not show any velocity gradient. So this is the basic category. So here it is non-Newtonian fluid category, and here plastic fluids, thixotrophic fluids. So this is the way. So generally whatever we encounter in our real life, maximum either, so mostly from mostly from Newtonian category, but non-Newtonian also exists, but plastic and thixotropic is very rare condition. So some example you might be seeing, the printer sink is a category of some thixotropic fluid, and a human blood may be said as non-Newtonian category. So like this, the fluids generally which are very rarely seen fluids comes under non-Newton. Generally if you take air, this water all comes under Newtonian category of the fluids. And another category, so another property, so which we are going to discuss is bulk modulus. So which is very important in defining low speed aerodynamics and high speed aerodynamics category. So bulk modulus generally represented with K, so which is written as dP by dV by V. Change in pressure divided by change in volume to original volume. Okay, so this bulk modulus is the inverse of compressibility. So generally if you take compressibility, it is simply, you can write it as 1 by K. So because of which the equation becomes as minus dV by V by dP. So here, since V gets cancelled, here we have pressure in the denominator. So units will be Newton per meter square in the denominator. So finally compressibility units will be meter square per Newton. So meter square per Newton are the units of compressibility. And here the compressibility is very important factor, so which we use in our upcoming video lectures for defining various kinds of categories of fluids. In the sense aerodynamics related, we are going to discuss based on many factors based on compressibility. So this is compressibility, so which is the unit is meter square per Newton. So simply it is why we have got negative symbol. So the explanation is here. So whenever you apply some pressure on a fluid, so that applied pressure in turn makes the fluid to decrease its volume. So the rate of decrement of volume. So because since volume is decreasing, so minus symbol shows the decrement in volume here. So on application of some pressure, there is a decrement in volume, so because of which we have got negative symbol. So that's the explanation for the negative symbol. So just it's a practical application. Whenever you apply, take this duster, I am applying some force, some pressure. So on application of pressure, so its volume is decreasing. So decrement in volume is the negative symbol. So these are the important fluid properties. Now based on these fluid properties, we are going to see the types of fluid flows. So there are many varieties of fluid flows. So mainly I am going to discuss the fluid flows which found very important in aerodynamics point of view. So in aerodynamics point of view, so I am going to write the important types of fluid flows. So first one, uniform flow, non-uniform flow. Steady flow, unsteady flow. Fifth one, laminar flow, turbulent flow. Seventh one, viscous flow, inviscid flow. Ninth one, compressible flow, incompressible flow. 11th one, rotational flow. Irrotational flow. So in addition to this, we have two-dimensional flow, three-dimensional flow, so which I will discuss orally. So these are the main categories. So you can form this as pairs. So one category here, two category here, three category, four category, five category, and six categories of flows. You can form as a pair. So just pair in the sense these two are opposite to each other: uniform, non-uniform, steady, unsteady, laminar, turbulent, viscous, inviscid, compressible, incompressible, rotational, irrotational flows. Now we will see one by one. So what they are and how they will be used in different contexts. So here uniform flow and non-uniform flow. So uniform flow. So uniform in the sense some parameters. So which are basically the fluid flow parameters are remaining uniform. So remaining uniform with respect to what? With respect to what they are remaining uniform. So uniform flow in the sense the fluid flow properties, especially there are five major fluid properties. So we have discussed just now. So pressure, density, velocity, temperature, and viscosity. So these are the majorly five fluid flow properties. Okay. So every fluid flow property definitely will depend upon the sum of this either one of the six categories of this fluid flows. Okay. So now if you take uniform flow, non-uniform flow category, so here mainly considered parameter is velocity. Velocity generally, velocity is indirectly dependent upon pressure, pressure is indirectly dependent upon density. So velocity, if the velocity, mainly if the velocity, or you take any other parameter like pressure. So the major component of fluid flow properties, if do they remain as constant with respect to location, so such a kind of flow is called as uniform flow. With respect to location in the sense, for example, I am taking a flow which is passing from left to right in x direction. So a fluid flow is passing from left to right in x direction. And here this is my considered area of the fluid flow. So fluid flow is happening in this length and in this height. Okay. Now if I measure the velocity at any point along this length and at any height along this area, so any length or any height, if the velocity parameter is remaining constant, same everywhere, such a kind of flow is called as uniform flow. So especially, so let us say x parameter we have considered here, x direction. So dou v by dou x. So here velocity is not changing with respect to x direction. So velocity is remaining constant. So the differentiation of a constant is 0. The differentiation of constant is 0 because velocity is remaining constant with respect to x direction or with respect to y direction. So any direction you may consider. So because of that, the flow will be called as uniform flow. It is uniformly flowing. Okay. So mostly the straight line flows in real life will be maximum of uniform nature. Because you just think, whenever you want to take a directional change, whenever you just want to change your direction, so maximum you need to change your velocity vector. So velocity vector you need to change. Without, that means I am talking linear velocity. Angular velocity you may remain same, it may remain constant, but linear velocity definitely may be changed to maximum context. Okay, if you want to take a streamline pattern, so definitely linear velocity has to be changed. So without possibility of change in linear velocity, It's difficult to take a curved path, and the two highly curved paths are very difficult. So that's why mostly straight line flows can be considered as uniform flows, provided if the velocity variations are very negligible. So definitely velocity variations will be existing. So without variation of velocity, there is no possibility of flow, because friction always plays a major role. Friction will be there and viscosity will be there, but the changes can be considered as negligible. So mathematics allows us some provision. So generally mathematical errors less than 5% are negligible in context of analysis of results. So if your value of velocity change within your considered length or height is less than 5%, simply you can consider it as uniform flow. And if it is not happening, it is non-uniform flow. Okay, so one is the opposite of the other. So uniform flow, the parameters remaining constant with respect to one direction. So that's all about uniform flow and non-uniform flow category. So next one, steady flow, unsteady flow. So steady, generally we use in our real life context. Be steady. So be steady means, so you should not have any change in your position. Be steady, we will say. So generally you should not change any position. Here you should not change any position in the sense you should not change any property. The fluid should not change any property. With respect to what? Here the distance parameter came, x or y. Then here what parameter comes? Time parameter comes. So here the time parameter is the important parameter, so with which the fluid properties are remaining constant. You take any fluid property if you take, so if that fluid property is remaining, suppose you are observing certain flow, a flow is passing like this and you are here, staying here, and based on time t equals to 0 to some t equals to 10 seconds. So you observed a flow, okay, and in this location, if the fluid properties for 10 seconds, you are getting, every second you are taking a value, and every second if you are getting same pressure or same density or same velocity or same temperature or same viscosity, then such a kind of flow you can call it as steady flow. That means the fluid properties, for example I will take pressure. So the fluid properties are remaining constant with respect to time. So the differentiation of a constant is 0. The differentiation of a constant is 0. Hence, so you can write any property if it is differentiated with respect to time, and if you are getting 0, then that property is remaining constant with respect to time, and hence you can call it as a steady flow. Okay, so condition is fluid properties should not change for a given period of time. So in that period of time you can call the flow as steady flow. And if it is changing and if it is not remaining constant, then the another way of representation is any property you take which is not equals to 0, so you can call it as unsteady flow. Unsteady flow, steady flow. Then another important category, laminar flow, turbulent flow. So laminar flow, turbulent flow, this is a real life experience which we might be observing mainly in water channels. So what is laminar flow? So laminar flow generally defined as a flow which is happening in orderly manner. So orderly arranged manner, if a flow is happening, so such a kind of flow is called as laminar flow. Okay, for example, a flow is taking a curved path like this. So if you take the trace of the fluid molecules, all the fluid molecules are following a perfect path like this. There is no disturbance. Okay, so such a kind of flow is called laminar flow. And even in uniform flow, same category. So uniform flow by default it will become a laminar flow because it is orderly arranged manner. So any flow which is happening in an orderly arranged manner, if you trace the path of the fluid molecules, if you can trace the path of fluid molecules and if they are in perfectly orderly arranged manner, such a kind of flow is called laminar flow. And turbulent flow, so turbulent flow, so which is happening in a unorderly manner or zigzag manner. Okay, for example, after taking turn, the flow has created some kind of whirling or vertices here. So such then till here the flow is laminar, and after this the flow is turbulent. Okay, so laminar flow up to this region, and thereafter it is turbulent. So turbulent flow is uneven flow which is having random motion and different kinds of flow properties which they change randomly with respect to space, with respect to time. Space in the sense xy location. So fluid properties continuously change with respect to location as well as with respect to time. So such a flow is called as turbulent flow, and turbulent flows are very difficult flows in aerodynamic and CFD analysis. So they create lot of problems in estimating fluid flow properties, because the fluid flow properties never remain constant as they vary with respect to location and with respect to time in spontaneous manner. So because of this, turbulent flows find to be very difficult. Okay, generally whatever we see, the channel flows, water flows in canals, so all these kind of flows, generally whenever they are taking a direction or whenever there is a disturbance, so generally you can see this kind of laminar flow. When water is flowing in a straight path, so generally you can observe a kind of laminar flow. So this is turbulent flow, this is laminar flow. So whenever a disturbance is kept in a laminar flow, then it easily becomes a turbulent flow. Okay, so disturbance makes a laminar flow to become turbulent flow. And viscous inviscid, this is just for theoretical assumptions. In real life, we said just now we discussed. So ideal fluid. So ideal fluid is the fluid which does not have either viscosity or surface tension. Such kind of flows never exist. Okay, but for theoretical purpose, because theoretical and numerical purposes, viscous term is avoided, because viscous term is the most complex term in partial differential equations, so which create a lot of complexity in equations and which increases the time for getting the result. So computation or calculation time, it increases. So for that purpose, in certain cases where viscosity is not a predominant factor, so viscosity is neglected and fluid properties are estimated. So when you neglect the viscosity, such kind of fluid is called inviscid fluid or inviscid flow. Okay, when you are neglecting the viscosity and estimating the result, such kind of analysis is called inviscid flow analysis. But real life, all the fluids are viscous fluids. Every flow we have some viscous nature, we cannot neglect the viscosity, but for some assumptions which falls under the category of less than 5%, you can neglect the viscosity and you can straightly go for inviscid flow, which reduces your computation time or calculation time to get the result very easily. So such a category, so if you consider the viscous nature, it is called viscous flow. If you neglect the viscous nature, it is called inviscid flow. Then another category, compressible, incompressible flows. This is a very big topic. So especially as aerodynamics engineers, we should know clearly what is compressibility. So compressible flow, incompressible flow. So whenever on a fluid a pressure is acting, so definitely the pressure makes its volume to squeeze. Squeeze in the sense, definitely there will be change in volume of the fluid. So liquids, of course, they change very slightly. So liquids are generally considered as incompressible because they are very slightly affected by the change of pressure. But coming to gaseous, so they are very much affected by acting upon pressure. Okay, hence the gases are highly compressible in nature. So whenever they are acted upon by pressure, so they have changes in volume. Okay, changes in volume leads to changes in density. Okay, so density, directly we are not dealing with the compressibility factor, which is 1 by k. Okay, so we are indirectly dealing with density. Okay, so for this category of the flows, density is the major property. Okay, so if density changes are very highly dominant in a fluid flow. Such a fluid flow is called compressible flow. And if density changes are very negligible, probably less than 5%, then those category of the flows are called incompressible flows. Generally, all liquid flows, especially water flow, will come perfectly under the category of incompressible flow. Okay, and gaseous flows. So, for example, airflow. So now, very important topic in aerodynamics. So when you call airflow as a compressible flow, when you can call it as an incompressible flow. Okay, so I told mathematics allows error up to 5%. Okay, so in real life, yesterday we did, in a previous video we discussed. So a flow always flows from high energy to low energy, especially the gases that takes energy in the form of changing pressure. Okay, so they flow from high pressure to low pressure. So pressure changes are always accompanied by density changes. Pressure change, definitely it will reflect its action on density. So immediately density will change. Okay, so any fluid flow, in order to happen, definitely there should be a pressure change, and if pressure changes, density change. So you cannot call any fluid flow as incompressible flow. Truly speaking, you cannot call any fluid flow as incompressible flow. Fluid flow only I am saying. Okay, so now what is the category is, suppose if the density changes in a category of the fluid flow are less than 5%, you can call them as incompressible flow. And if density changes are accounting to greater than 5%, then you can call them as compressible flows. So now for air, what is the condition? So for air, generally at STP conditions, standard temperature and pressure conditions, up to Mach number 0.3, up to m equals to 0.3, you can consider as incompressible. So under STP conditions, which approximately corresponds to 100 meter per second velocity. So for airflow, up to Mach number 0.3, which corresponds to velocity equals to 100 meter per second under standard temperature and pressure conditions, you can consider till that region as incompressible flow. So density changes are not that much affecting the result. And if your Mach number for the airflow is greater than 0.3, m greater than 0.3, then definitely your velocity also will be greater than 100 meter per second, and such a velocity you have to call it as compressible flow. So this is incompressible and this is compressible category. So this is applicable, remember, only for airflows. Okay, so airflows, generally atmospheric airflows, and if you are taking a particular gas, again we have to calculate based on specific gas constants. Okay, so for particular airflow, atmospheric airflows, up to Mach number equals to 0.3 under STP conditions, which is corresponding to 100 meter per second approximately velocity. So till that region you can consider it as incompressible flows, and here it comes around greater than 0.3 Mach, so which is greater than 100 meter per second. So generally if you talk, the vehicle speeds are expressed in kilometers per hour. So here you can call this velocity multiplied by 3.6, you will get around 360 kilometer per hour. So if any vehicle traveling less than 360 kilometer per hour, you can use straightly the incompressible flow equations. And if any vehicle traveling greater than V equals to 360 km per hour, you have to consider compressible flow equations. Okay, so all the automobiles comes under incompressible flow category. And for example, road vehicles like trains, bullet trains, maglev trains, if you take, they cross the region 360 km per hour. There are certain trains in France which can cross 400, 450 km per hour. So for those trains, compressible flow aerodynamics we need to consider. But for automobiles, straightly we can go up to 360 km per hour, even for race car aerodynamics also. So generally race cars also cannot travel more than this, I think so. So you can use the incompressible flow assumptions for all the automobiles. And if you have a wind tunnel in your university or college, you can straightly put an automobile and you can do testing, you can find the CP values. Okay, and if you have a supersonic wind tunnel, and first case is low speed subsonic wind tunnel, and second case if you have a supersonic wind tunnel, then you can make calculations taking atmospheric vehicles like aircrafts, rockets, and beyond atmospheric vehicles also, which travels more than Mach 2. So you can use the wind tunnel, supersonic wind tunnel estimations, and you can further do the experiments and generate the results. So viewers, that's all for today. Thank you for listening. Do subscribe to my channel and share my videos, and keep in contact for more and more lectures. Thank you.